Hey everybody, welcome to today's Kubernetes Masterclass. Really happy to have you all join us today, wherever you are at in the world. We are just getting started and we have quite a few people who have registered to attend today. So I just want to take a couple moments to allow more people to join the line. But while we are waiting for them, I want you all to know that this session is being recorded and you will get the recording and the slides after the training. We do have a lot to go over, and we have about 75 minutes scheduled. But in case you need to drop early or for whatever reason you can't make the whole session, then don't worry, you will not miss anything, as we'll be posting the recording online and sending it to you all in email. So let's go ahead and get started. We're going to be talking about block storage and distributed SQL today. My name, as a way of introduction, is Matthew Shear. I'm a marketing manager here at Rancher. I help host these sessions and many others, which I will talk about in a moment. So you will see me there. You can sort of consider me a point of contact, a reference, or resource at Rancher if you are looking for slides, for recording, for a particular topic. You're trying to find more material. Please don't hesitate to reach out to me, or if you have another question, don't hesitate to reach out. I'm happy to connect and continue the conversation. You can get to know me or reach me at Matthew, just simply at Matthew at the Rancher user Slack. And I'll talk about the Rancher user Slack in a moment. Or just email me, Matthew@rancher.com. But the man who's really going to be doing the heavy lifting today is Sid Chowdhury, SVP at Yugabyte. Sid, are you there?
I'm here, Matthew.
Okay, great. Please forgive me if I butchered your name. The hard things about hosting these is just getting that pronunciation. But yeah, we have a lot to go through, and I'll let Sid introduce himself a little bit more as we go along. So a couple housekeeping guidelines before we jump right in. We have about 75 minutes scheduled. These can go short, just depending on how the questions that we have, how much you all want to learn. So we do our absolute best to stay and answer every single question. Please go ahead and put your questions into the chat. We try to be responsive to what you all want to learn. My only request is that you just try your best to keep your questions on topic to what Sid is presenting about. If it's not, or for whatever reason it's just we can't answer, then I will refer you to another resource. And if you want to keep your questions private, just let us know. Otherwise, we will answer them aloud for everyone's benefit. As I mentioned, this session is being recorded. It'll be posted on YouTube, so you can check it out there. We put all of our online trainings, our online meetups, our master classes on YouTube. So there's a ton of video content there to understand Kubernetes, understand Rancher, understand Docker, and lots of other cloud native technologies. So please do check those out. You'll see this recording will be posted there after the session as well. And as I mentioned, we do have a Rancher user Slack, which is a fantastic way to get plugged in with the Rancher community, people who are trying to solve similar problems as the ones that you are facing. So I highly recommend joining this. Totally free, free and open to the public. We do have many Rancher engineers who help answer questions here as well. So you can just go to slack.rancher.io and join. I have thousands of members and hundreds of people asking and answering questions every day. We also have a channel just for masterclass, which is pound masterclass. So sometimes we'll post extra files there, notifications, and things like that. So if you're interested in this series, then you can join that channel. And we also have upcoming classes coming up. Every week we do a weekly Kubernetes and Rancher training. Unfortunately, tomorrow's is postponed until next week, but please do check that out. If you are new to Kubernetes, if you are new to Rancher, it is a fantastic way to get to know Kubernetes. We go over Kubernetes components, architecture, understand what Kubernetes is for, and then we talk about what the Rancher management server adds on top of Kubernetes to extend its advantages. And we also have a masterclass next week on Open Policy Agent and the new Gatekeeper integration that just launched with Rancher 2.4. So that should be really, really interesting. So check those out. And so now, without further ado, I'm going to pass this presentation over to Sid, so we can get into the meat of the material and why everyone is here. So I'm going to make you the presenter.
Hello, everybody. Really excited to be talking to the Rancher community here. My name is Sid Chaudhary, and I'm SVP product at Yugabyte. And today we're going to dive into the details of how to use a distributed block storage technology like Longhorn with a distributed SQL database like Yugabyte DB. And we'll go into a fair amount of detail in both. So without further delay, let's dive in. Um, to all the audience here, I'm pretty sure they understand what SQL databases are. SQL stands for Structured Query Language. It's the lingua franca of relational databases for almost 40 years. It helps us model, tables, rows, columns, relations like foreign key constraints, do select queries that join multiple tables. It's a very well understood database client language that applications have used since time immemorial to store and manage transactional data. Well, SQL is also used in OLAP these days. So what is distributed SQL and why it is exciting? Distributed SQL is a revolutionary OLTP database architecture. And why do we consider it to be revolutionary? Let's take it to the next level. First of all, it is SQL, so you can model relations and you can do all the same, ACID transactional constructs like begin transactions, read and update multiple rows of multiple different tables, and then you commit transaction. Very, very powerful paradigm from an application programming standpoint. However, these both SQL and ACID transactions have not been available in the distributed form factor for a long time. And that's where distributed SQL comes in. So what does distributed actually mean? Distributed means that a single logical SQL database is now powered by multiple nodes in a cluster. And irrespective of however many nodes in the cluster, there is that single logical SQL database. The benefits to the application developer are threefold. First is ultra resilience. Since the data is essentially replicated internally in multiple different nodes, the loss of, let's say, one node doesn't bring down the cluster. You can continue to do your reads and writes as if nothing has happened from an application standpoint. Very powerful concept, especially when we talk about the modern cloud and cloud native architectures, where failure is essentially baked into your equation. Some infrastructure, whether it be compute, storage, network, partitions, all those things will happen guaranteed. How, as infrastructure architects and application programmers, we deal with is our challenge. So that's number one. Second benefit of this distributed form factor is massive scalability. We have always had scalability in NoSQL databases, where you can just add new nodes if you want to increase write throughput in the system. The way internally those databases work is they rebalance the cluster by taking some amount of data that were present in the previous nodes and moving to the new nodes that came by and so on. This aspect of horizontal write scalability is a unheard of concept in SQL databases like Postgres, MySQL, Oracle, SQL Server, and so on. But the new distributed SQL architecture allows this sort of massive scalability. You can expand and contract your clusters at will. And that allows us to not over provision our infrastructure, right size it, and if needed, go beyond by adding a few more nodes. But once it is done, let's say our Black Friday and Cyber Monday is done, we bring back the cluster to its original configuration. So that's the second benefit. Third benefit is a very fascinating benefit because it's something that it was, I would say, previously unimaginable. it's around geo distribution. So today the modern cloud actually gives us so many different data centers distributed all around the globe. And if we take the three, Amazon, Google, Azure, I think the number of data centers they have is more than 100. So as application architects, how do we exploit these data centers that are available to us now almost as a commodity? We can just programmatically bring up um, our instances, our applications in those data centers at a moment's notice. But how do we architect applications to take advantage of that new data center, geo-distributed data center capacity? So one thing that has always been challenging is the database, especially the relational database, which has been stuck to a single node inside a single zone, inside a single region of a single cloud. No longer. The distributed SQL, we can actually take our nodes and distribute them across multiple regions, and there are multiple data centers, and there are multiple such configurations possible. You can do a traditional 2 data center architecture that we have been all used to from the monolithic SQL days, or the more exciting deployment is around a globally consistent 3 data center architecture, where 1/3 of your data resides in each one of those 3 data centers, and any writes into one are instantaneously replicated or available on the other side, on the other 2 data centers. The benefit is that now we can tolerate region level failures. We can bring data closer to our users who are local to those regions, as a result reduce the application latency and build very interesting, very exciting user experiences, like your the Uber's car tracking application, which sort of clearly shows us where the car that we have asked for is actually on its way, right? So with that as the architectural paradigm, um, let's see. I mean, I've already touched on some of these things, but these things will make more sense now in this context. I took those 4 features, and now I have mapped it to the needs of the 2 big uh, layers that actually hold up our applications. So as microservices, we need ability to do flexible query in our applications. So that's where SQL language, its relational constructs, its ACID transactions come into play. As if our microservice is very successful, then we'll need such scalability because more users are hitting that, right? On the other side, now that we're in the multi-cloud Kubernetes era, we need resilience in our infrastructure, in our databases. If things fail, then our database should still self-heal and continue to provide its guarantees to the applications, as if nothing has happened. As well as the last but not least aspect is geo distribution. So distributed SQL is sort of sitting at the center of these, I would say, 4 needs that are being brought on to us, and allows developers to write applications faster because they understand SQL. They understand how to model complex applications with that. And it also helps the operations engineers because it allows them to deploy these applications into the modern cloud native stack much easily than ever before, by virtue of technologies like Kubernetes and Longhorn. The end benefit is obviously to the business. We build technologies so that we can actually make an impact to our business and our end users. And if our dev teams and our ops teams are able to do more in less amount of time, then the business velocity naturally increases. So with that, let me introduce you to Yugabyte DB. Not sure how many of you have heard of the technology, but we are a high performance, open source, cloud native distributed SQL database that is actually fully wire compatible with the PostgreSQL SQL dialect. So let's take each one of these aspects a little bit deeper. First is high performance, which comes in the form of architecting a underlying storage engine that is actually modeled, inspired from Google Spanner, which is Google's relational database that's now available on the Google Cloud, and making sure that it can serve queries in extremely low latency, even if there is actually distribution of data going on underneath the surface. Secondly, we're built for the cloud native era because we can understand the dynamic nature of the underlying infrastructure that, for example, Kubernetes brings to bear, where the pods can get auto rescheduled to a different node with almost no notice, right? That's what Kubernetes does. Its job is to efficiently utilize the CPU, memory, storage resources that are available to us, and by using internally replication, which is actually based on Raft distributed consensus, and as well as making sure that we do auto rebalancing of the data without impacting the application layer, makes us very, very suitable for the Kubernetes kind of deployment, and integrate very well with the cloud native ecosystem projects like Longhorn. Last but not the least, we are a fully open source project, 100% Apache 2.0 license. You are welcome to give it a shot, give us feedback, and so on. We'll give you some more pointers towards that. Before I move out, just a note about the name. Yuga in Sanskrit means eons or ages, and byte obviously means the unit of data. As a distributed OLTP database, it's Yugabyte DB's job to make sure that your precious business critical transactional data can live across eons, across ages, and remains protected from faults, can scale, and so on. So hopefully that makes sense. Just a quick slide on how the architecture of such a database looks like. There are 4 nodes in this architecture scheme. Each of the nodes acts as the data server, which is the YBT server layer. And inside that, first is the notion of automatic sharding of tables. So we take any table and we divide it into tablets, which is called also known as shards. And we make sure that those tablets are distributed across all the nodes available. So for example, if table 1 is being divided into 4 tablets, tablet 1, tablet 2, tablet 3, tablet 4, they are being put in 4 different instances, so that when they are serving application reads and writes requests, they are actually using different compute and storage resources, rather than contending for a single instances compute and storage resources. So that's the benefit of doing sharding automatically. Second comes replication. So each tablet, like let's take tablet 1, is also replicated 2 times into 2 different fault domains. For example, tablet 1, the primary of tablet 1, called as the leader, is present in node 1, but the follower replicas are present in node 2 and node 3. Similarly, tablet 2's leader is node 2, but its follower replicas are present in node 1 and node 4. You get the idea. We do this again automatically to make sure that if for some reason we lose, let's say, node 2, then we lost the leader replica for tablet 2, and we lost 2 follower replicas of some other tablets. The follower replicas are sort of immaterial, because as long as we have 2 replicas available, we can continue to progress in the Raft-based distributed consensus model, very similar to how Kubernetes underlying metadata is stored in etcd, which also uses Raft. The more interesting one is the loss of this leader replica tablet 2. That's when, if this node is lost, the remaining 2 replicas of tablet 2, which is one is present in node 1, another is present in node 4, they run a auto election using the same Raft protocol, and one of them becomes a leader almost instantaneously. And as a result, writes can continue to progress on that tablet immediately thereafter. So this brings in a self-healing nature into the system, so that infrastructure failures, which are increasingly common, can be continued to be tolerated. So on top of this sharding and replication design is a distributed ACID transactions architecture, where a distributed transaction manager sits on each one of these tablet servers, and it manages multi-row transactions on your behalf using a two-phase commit protocol. Okay. And application clients speak to it in using PostgreSQL drivers because we speak PostgreSQL. Underneath this data service, the YBT server service is a config management server called the YB master service, where the metadata about the cluster, which means how many databases are there, how many tables each one of those databases are, each table is sharded how many times, and where are those shards located. All that information is actually present in this special tablet called syscatalog, and that's present in this YB master service. And that's where clients initially connect to, which they have let's say they have never connected to the cluster. They initially connect to that, and but again transparently, because they don't know the presence of YB master. And then they bring in this shard metadata information and keep it with themselves, and thereafter the YB master service never comes in the critical IO path. So this allows the system to essentially scale as big as we want, tolerate failures automatically because it's self-healing, while while providing the full language constructs of the SQL language back to the applications. So that's the value add that's of the architecture. So now, why is this kind of an architecture relevant or sort of very useful in the Kubernetes form factor? So before we go there, let's look into how does this maps to Kubernetes. So we have similarly nodes, right? Let's say there are 4 nodes here. Our Helm chart, for example, automatically creates 2 stateful sets on your behalf. One is this 3-pod YB master stateful set. That is not very interesting. The more interesting is the sort of the infinitely scalable T-server stateful set that is actually responsible for all your data. And all the things that I talked about are now starting to becoming applicable in the Kubernetes form factor. The only thing that happens, and I'm pretty sure you all can appreciate it, is it compared to the VM world or the bare metal world, and compared to the Kubernetes world, the lifetime of a single pod in one of those in any of these stateful sets is actually much smaller. So Kubernetes has a high chance of rescheduling one of these Yugabyte DB pods to some other node, but data has gravity. The data was previously present and mapped to the underlying persistent volume. So if the pod gets rescheduled to some other place, how will that pod have access to the same data? So that is what we solve by doing 2 things: replication, which is baked into the cluster, database cluster, as well as doing automatic rebalancing of data. So whether they are unplanned failures or sort of rescheduling by Kubernetes does not matter. You continue to receive all the data available to you as if nothing has happened in the underlying infrastructure, and you means the applications. Secondly is, let's say if we add a few more nodes into the Kubernetes cluster itself, then the database cluster knows that now it has more capacity available, so it will start moving some of the pods and which have their own replication logic into this new nodes that have now been brought forth. As a result, you can now exploit the new resources that you have brought to bear into the database cluster. Last but not least, by dividing into the core database stateful set, which is the YBT server, and the config management database stateful set, which is the YB master, you can scale them independently. The YB master is typically remains in a sort of a 3-pod architecture, very similar to how HCD remains inside a Kubernetes cluster. But the YBT server stateful set can scale as big as you want and can scale down as small as you want, with a minimum of obviously 3 pods or 3 replicas. So distributed SQL combined with Kubernetes allows us a lot of flexibility when it comes to managing transactional data. Let's bring in Longhorn to the equation. What is Longhorn? Again, I'm pretty sure most of you have seen Longhorn in action, given that it's one of the more popular Rancher projects. But here is a quick introduction. It's a highly available persistent storage for Kubernetes that Rancher actually donated to CNCF as a sandbox project, I believe last year. The key benefit of Longhorn as compared to the likes of, let's say, Rook, Chef, and things like EBS, let's say OpenEBS, is that it's a very lightweight and intuitive approach to storage management, which has been built with DevOps teams like you in mind, as opposed to storage administrator experts who live and breathe in the storage world day in and day out. So that allows people to get started easier, deploy in various public cloud and Kubernetes form factors much more easily than some of the other technologies. So what is the benefit of bringing a distributed block storage like Longhorn into the equation with distributed SQL and Kubernetes? Well, from a deployment standpoint, each one of those persistent volumes will now become managed via Longhorn, right? Because Longhorn is going to provide us the storage class in this equation. So the benefits are a fewfold. First of all, if you realize from a distributed SQL workload standpoint, if we use lots of local PVs as opposed to remote PVs, there is a benefit around latency, because every data is essentially present right there in the node where my pod is running in, and I have almost never to access outside that pod and bring network into the equation. As a result, local PVs deliver higher performance, lower latency. But the challenge with local PVs is that you are obviously dependent on the replication that is happening at the database layer to keep your data protected. What if we can add another layer of protection into such a PV persistent volume management by using Longhorn? That will be awesome, because now we can essentially bring down our RPO, RTO when things go bad. For example, in a let's say my Kubernetes cluster altogether has gone into a disaster mode, and I need to recover from another cluster. And that is a problem that Longhorn can easily solve, because it is very good at cross-cluster DR. That's number one. Secondly, it is also very good at doing node rebuilds in a multi-cluster environment. So I was talking about geo-distributed deployments being a forte of the distributed SQL database, like Yugabyte DB. So imagine we have such a database cluster running in 3 regions, and each region by definition is running on an independent Kubernetes cluster, and hence it's a multi-cluster deployment. And one of the node in that region fails. Now, as a distributed SQL database, we will automatically rebalance. We'll have to pull data from the other region, because the replica for the node that we lost, the leader tablets that we lost, is actually present in the other region. So we'll bring that in. But with using Longhorn, since the block storage had already kept copies of the data, it can help the distributed SQL database recover even faster by reducing the rebuild data pull from the other region, which incurs wide area network latency, right? So the end benefit is that you can derive higher performance on the distributed SQL side, and you can get better RPO, RTO by essentially banking on Longhorn to accelerate the rebuild of the nodes whenever something goes bad. It's clearly a win-win situation here. Okay. So what have we learned so far? Well, we have seen that in order for us to build modern applications at a very fast pace and deploy them on the cloud native infrastructure that we've all come to appreciate and love, we need our the application and infrastructure stack to become very resilient and flexible, right? And that comes from by powering our microservices with the combination of Yugabyte DB as the SQL database, Longhorn as the distributed block storage, and Kubernetes as the provider of compute storage network, the underlying IaaS layer, while leaving management of the entire Kubernetes itself and the stateless and stateful apps on top of that via Rancher, right? So this kind of a resilient, flexible, and open source cloud native stack can essentially help us build applications faster. That's the goal. So this is a logical point for me to take a pause. And before I dive into the lab itself to see how things are in action, Matthew, if there are any questions, we can take them now.
Awesome. Thanks so much, Sid. Yeah, there are several questions. Let's jump in. Here, this is from Barbaros, who says, how does Yugabyte distributed SQL satisfy CAP and ACID compliancy at the same time?
Perfect. Excellent question. That's one of the first questions people ask. So in the CAP theorem standpoint, let's look at what CAP says. CAP says that in presence of failures, which is partitions, which is the P, you can have either C, which is consistency, or availability, which is A. When there is no partition, you can have everything. You can have both consistency and availability. In the CAP theorem model, Yugabyte DB is a CP database, which means that in presence of partitions, Yugabyte DB chooses consistency over availability. And that's very different than the traditional NoSQL architectures like that of Cassandra, for example, where availability comes paramount, right? We follow the model of Google Spanner and HBase, the sort of the databases that came before us, where the consistency of the data, the correctness of the data stands first and foremost, even if we cannot guarantee 100% availability. However, we can actually tune the availability to come to very close to 100% by doing the self-healing nature that I talked about, where when there is a node failure, it leads to loss of some leader tablets, and those lost leaders are brought back in the two remaining replicas by running an automatic leader election. And so the net penalty, in a way, to the application is for those 2-3 seconds when the leader election is going on, for only those lost leader tablets, you cannot do writes into the system. Because if the database lets you write into the system, it cannot ensure the consistency of the data. It cannot put the data in enough different fault domains in order to guarantee that your data is kosher. As a result, it disallows writes during those 2 to 3 seconds. But beyond that, it heals automatically. So it is CP database with a very high availability. Again, very similar to the Google Spanner architecture that Yugabyte DB is inspired by. Now
Awesome.
comes ACID transactions. So CAP theorem is what is known as the theorem for understanding linearizability, which is also can be thought of what happens to a single row in the system, right? ACID transactions are predominantly about multiple rows and how concurrent access into a single row or those multiple rows are handled. And in that case, D is obviously guaranteed because it's a database, otherwise there is no point. The more important ones are A and I, atomicity and isolation. So atomicity is again handled by the distribution transaction manager that I talked about, where it controls, it does the coordination of the multi-shard transactions on your behalf. And isolation level is what guarantees what reads can be served while there are concurrent transactions working on the database. And for that, Yugabyte DB provides 2 levels. First is the serializable isolation level, and the second is the what is known as the snapshot isolation level, or in the PostgreSQL parlance, it's called read committed. I hope that makes sense.
Okay, thank you. Thank you.
Yeah.
Yeah, there are several more questions. Let's jump in before we get to the demo. This next one's from Christoph, who says, "What's the difference between Yugabyte and Vitess?"
Yes, excellent question. Good. We have a very informed audience. So Vitess is a CNCF project that is actually a automatic MySQL sharding layer. So your database is still MySQL, but Vitess is a layer on top of that MySQL that allows you to automatically partition your data, which is shard your data into completely independent instances of MySQL. Now, if you look at what did I explain in the distributed SQL architecture, it's sharding, replication, and multi-shard transactions. That's the foundation of the distributed SQL architecture. So in the Vitess case, you get the sharding because that is what Vitess does, that layer of sharding that it provides. What it doesn't do is the next two. You are still relying on MySQL's traditional master-slave replication architecture in order to manage fault tolerance of your data. Second, which has its own penalties around how consistent reads can be served in the system and how much data loss is allowed in the system. And second is multi-shard ACID transactions. You cannot actually do things like serializable or even snapshot isolation level multi-shard ACID transactions in a Vitess, because each instance of MySQL is completely unaware of the other instance of MySQL that is present in a Vitess cluster. So if you have built an application where you can neatly partition the data in such a way that you never need to do more than a master slave replica, and B, you never need to do cross shard transactions or cross shard ACID transactions, then Vitess is a good solution. Otherwise, it's not a good solution. You'll pay a heavy penalty as time progresses.
Okay, thank you. Let's take one more, and then why don't we go into the demo, and then we can take more questions.
Sure.
So this one is from Fabio, who says, "Is Yugabyte DB a drop-in replacement for Postgres, SQL, MySQL, etc.? Is it that easy to swap one technology for another, or does it require a complete rewrite of an application to use it? For example, could we just replace MySQL from a WordPress application with a Yugabyte DB?"
Wow, another excellent question. So first of all, we are not MySQL compatible. So it is if something is written with the MySQL dialect, then you are looking at writing it in the Postgres dialect for sure, because we are Postgres compatible. Now, can you replace Postgres with Yugabyte DB? As with everything, it depends. Postgres, we support a wide aspect of the Postgres language, syntax, and grammar, including even esoteric features like stored procedures, triggers, partial indexes, and so on. However, I think it would be incorrect for me to say that the 100% of the grammar that Postgres has developed over the last 30 years is now already implemented inside Yugabyte DB. We are much, I would say, more compatible with Postgres than any distributed database out there, because actually we reuse the Postgres native C code in order to build our SQL query layer. So we have taken the open source Postgres project's upper half and reused to make it run on top of the distributed document store that is Google Spanner inspired. However, I would not be claiming that you can just magically drop every Postgres application that's out there and run it on Yugabyte DB. There will be some places where some of the language is not implemented, or also there will be places where you are actually beneficial to think a little bit more now that you will be running on a distributed form factor and model your schema slightly differently around how you model, let's say indexes, or how you model foreign key constraints and so on. But it is not as bad as doing a 100% rewrite.
Okay, cool. All right, great. There are quite a few more questions, but why don't we go ahead and get to the demo, and then we can wrap up.
We'll come back to it. Okay, perfect. So in the lab itself, there are 6 big steps. And the complete docs are actually already live on rancher.com at rancher.com blog 2020 Yugabyte. So you can look it up there. For the purpose of this particular lab, what I have done is I have completed the first 3 steps. I've configured Google Cloud correctly. I have installed Rancher on a Google Cloud, Google Compute Engine VM, and I have also created a GKE cluster using Rancher. Now, why did I do that? Because that is something that A, takes a little bit of a time. B, you already know all that stuff most likely by virtue being part of the awesome Rancher community. So we will focus on 4, 5, 6 more, but I'll still touch on what 1, 2, 3 look like. So first is, in order to use Rancher on Google Cloud, what we'll do is we'll create a service account for Rancher to manage the GKE clusters we'll create. So you go into Google Cloud Platform, you create a service account. There are a bunch of roles that are needed that are listed on the blog documentation that I showed you. It's as simple as that, nothing more to it. Create a Ubuntu VM instance with some CPU memory. The Rancher docs explain you how much is good enough. It shows what I used, right? And this is the VM on which we'll run the next step, which is the Rancher itself. So we'll then SSH into the VM that we created in the previous step. We'll just run the simple command sudo docker run -d Rancher, and the end result is that you will see Rancher's UI in front of you, where you have to set an admin password, and now you are ready to use Rancher itself. Then we'll go inside Rancher and we'll say add a cluster, and we'll pick the GKE Google GKE tile, because that's where we're creating our Kubernetes cluster. And the first thing we have to do is we have to upload the JSON file, which is also called a key in the Google speak, from the service account that we had previously created. This will then populate the next screen that you see here, because it has all the details that allow us to then model what kind of an GKE cluster we would like. And I have used N1 standard 8, which is our recommended for I would say basic production deployment on GKE. You can use smaller, then you have to just make sure that you are appropriately reducing the amount of resources that the basic Helm, the standard Helm chart that we'll use later on to actually deploy the Yugabyte DB cluster. That's all. Now comes the interesting part. We will actually install Longhorn into GKE using Rancher, and then on top of this, we'll install the Yugabyte DB cluster. So let me go into, let me see. Okay, so this is my Rancher console, and I already have 3 nodes of my GKE cluster. You can see them here, right? And if you go to persistent volumes, no persistent volumes because there is nothing, no stateful app has been deployed yet. If I go to storage classes, only the Google persistent standard disk is available, and I do not have any other projects or namespaces. You can see it here. I only have the default and the system. That's it. So this is a clean cluster at this point. We're ready to install Longhorn into this. So we'll go into the system namespace. And what we'll go do is we'll go into apps and we'll launch the Rancher app catalog. And here we will search for Longhorn. We'll bring up Longhorn. It has got all the information. Actually, we don't need to change any of the default config, at least for purpose of this lab itself. And we will simply launch it. What now is happening is Longhorn is actually going into the GKE cluster and creating its own resources on top of it, including a dedicated Longhorn storage class, which we'll actually use while installing the Yugabyte DB cluster. So we can go inside and we see that the status is ongoing. I guess it is active now. If we go to default, it's a little bit slow. Okay, go back and we go inside the cluster. Voila, we have our Longhorn storage class for use by stateful applications like Yugabyte DB. So now is the time to go into the GKE cluster and install Yugabyte DB using the Helm chart. But note, I'm going to override the standard. If don't give this set storage master storage class, then the standard storage class gets used. That's what we don't want to happen here. We want to use Longhorn. So I have my terminal. What I'm going to do is, this is my GKE cluster. I'm going to connect to it. I'm going to copy the connection information. And I'm going to paste it so that my kubectl gets properly configured, and I'm ready to deploy applications into this GKE cluster. So for that, I have some commands. So let's start with one by one. First, I will add the charts repo for Yugabyte DB. It has been added. Now let me search what it looks like. Yes, it is present, and it is the 2.14 version, which is a recent version. Perfect. I will then first create a namespace for this database. And once the namespace gets created, I can actually do the Helm install. I'm keeping everything as is, not overriding any other parameter than the storage class, which is what Longhorn is. And now the Helm chart is doing its work. It's going into the cluster, the GKE cluster, and installing these things that I talked about. Let's touch on them again, because they will show up here. It's installing. This is a 3-node GKE cluster, so the 4th node is not here. It's installing one YBT server stateful set and its headless service with one pod each in each node, and one YB master stateful set with its own headless service with one pod each in the nodes. Right, so that allows us to essentially start using GKE for the purposes of the database cluster itself. We could have used any other Kubernetes distribution, including Rancher K8s itself. That's the beauty of the Kubernetes-based deployments, that the commands necessarily do not change. They're exactly the same, irrespective of where we are installing. So now if we go to our cluster, now we can see that few things are getting installed here. If I go into the projects and namespace, I can see that the YB demo project is getting the namespace is getting added. I can see some more memory, some more CPU, pods are getting used, and so on. Let's see what is happening on the Longhorn side. So if I go to system, and I go to Longhorn system, and then I go to index.html, which is, it now gives me the Longhorn UI. And there I can see that I have 12 volumes, and I have a bunch of available storage, and I have 3 nodes. Okay, so if I go to the nodes, I have those 3 nodes. They are the nodes of my GKE cluster. And if I go to volume, I can see that 2 minutes back, all these volumes have been created, right? You can see that all the volumes have been created. So now I can do a few things. I can actually go into, let's say, first let's see what the thing looks like here. It is still coming up, I guess. Let it come up. Once it comes up, what I wanted to do is just show you how the SQL features of the database work. It's very similar to what you have been used to in the past. I go into the Kubernetes section. All you have to do is essentially go to that namespace, to that T server, and launch this YSQL sh, which is essentially a fork of PSQL, the PostgreSQL shell, but it has been now customized for use inside Yugabyte DB. And once you go inside there, you can start issuing your standard SQL commands. We'll create we can create a database. We can we ship with a basic schema and a bunch of sample data. It's like a traditional e-commerce application where there are products that is being ordered via users, and those users also leave reviews for the products they have ordered. Very classic e-commerce schema. And then, even though it is underlying form factor is distributed, auto sharded, replicated, you can have even the nodes present in multiple different geographies, data centers, your SQL semantics remain constant, and which is where the power of the infrastructure like this is, where whatever you had used to, like, select count star from products, or do a select like this, or you can do join across tables. So that is still coming up. Let's see if I go in here. I can see that my nodes have, these are the storage volumes. Okay, I think it completed. I could have increased the timeout. So let's see if it gives me back the pods. Okay, it gives me 3 masters pods and 3 T server pods. Let's see, it gives me back the services. Okay, it gave me back the services. So the YB master UI service is interesting. I can take its external IP and I can go there to the 7000 port there, and that's the YB master console UI, admin UI, right? So we can see that there are 3 such masters. You can hit any one of them, does not matter, or you can hit it through the YB master UI service. And there are 3 tablet servers that are present. Since this is a single zone deployment that we went with, we are, all of them are defaulted. We could have overridden this, and then the zone level, region level, and cloud level rebalancing policies of replicas would have kicked in. Now we can actually do one thing. We can go back to this and see if we can log in. So I go here, I pick this up, and there you go. So I am gonna, let's say, just start. See, it's creating these tables for me because that SQL file is present in the pod already. It ships with the database just to show things how things work. I'll create 4 tables, SQL tables, and so on. And meanwhile, what we can also do is we can actually, now if we want to use, while the application developer is doing all the work, as the DevOps folks responsible for this cluster, we would like to make sure that these volumes have a backup available. So if I try to do this, I can do this, but I know that I haven't actually configured a backup target, and it's giving me the backup target is empty error message. So what if I could actually configure a backup target and set that in here? So if I go into the Longhorn settings, I can see that there is a backup target and backup target credential secret. So instead of continuing with this, what I will do is I will actually use, I'll quickly install a instance of MinIO, which is an S3 compatible, AWS S3 compatible object storage in the same cluster, and it got created. And I will set the values, and these instructions are there in the Longhorn documentation itself. So please go look at that. And I'll set these, right? And I save them. Once I save them, the backup tab is now available to us for usage, right? So now if I go to the volumes and I say, I want to take a full backup of all these volumes, irrespective of what my app developers are doing with them, I say, let's call it full backup, and April 22, is the date. I just put that, and now the system is taking backups on our behalf. We can actually even this was a on-demand backup. We could have scheduled this backup as well. So these are the powerful features that allow us to give this next level protection. Remember, the database itself doing its own replication. It's ensuring that your data cannot get corrupted. Your consistent data is actually served back to the application. But the ability to take backups at the storage level, store them in an object store, bring them back at will, provides this additional layer of protection, so that we are never vulnerable to any sort of big outages. Let's see, if you haven't done a multi-region deployment, but you actually want to tolerate region failures, then this is one way to do it, where you keep the backup off cluster in, let's say, an S3 or an NFS, and then bring it back up as and when you need, right? Now let's say if we ever to lose these, all you have to do is go to the backup and say restore lost backup. The software will take care of bringing this backups back into as persistent volumes, attaching to the previous nodes, and essentially bringing back your applications. So with that, I have reached the end of my presentation, if I remember correctly. Let me see. Yes, this is what we did, and this is what we ended up with, where Longhorn provides us the second layer protection on top of Yugabyte DB. So what's next? You're obviously very, very welcome in the Yugabyte DB community. Just like Rancher has a user Slack, we have our own user Slack. All our engineers are there to help answer questions and sort of guide you in the process of understanding distributed SQL's architecture, doing schema design alongside you for ensuring proper throughput, latency, workload operations. You can see all this Yugabyte DB in action on your own. If you go to, let's say, let me go to quickly download.yugabyte.com. You can actually run in various form factors, very similar. I think Rancher also has a very similar construct. You can run it on your local laptop. You can deploy multi-node clusters. You can fully sign up for the fully managed cloud, and so on. And we actually also write heavily on the distributed SQL blog around some of the underlying technologies. Just a quick show on that. There you go. Please join the community, give us feedback, run the lab yourself. It's available on this page, Rancher blog Yugabyte 2020. And that's it. I am done for the day.
Okay, thank you so much, Sid. Fantastic presentation. Thank you for that great lab. And I hope you're not done, because we do have quite a few questions. So let's jump into these questions.
Sure, absolutely.
All right, so this first one, this is from Martin, who asks, is Yugabyte DB still a relational database or a non-relational database like MongoDB?
So Yugabyte DB is actually a fully relational database with its Postgres compatible API. And also we have another API called Yugabyte Cloud Query Language, which is semi-relational. So while you cannot do foreign keys and you cannot do joins in the Yugabyte Cloud Query Language, you can do consistent secondary indexes, for example. The benefit in the two approaches is that the second API allows for extreme scale and even more low latency reads and writes, because you are almost guaranteed that your reads will not be touching multiple tables at the same time, right? Because the nature of that semi-relational construct is there. So yes, you can actually do both if you so desire.
Okay, thank you. Here's the next one from Ryan. So he asks, how does Yugabyte DB handles secondary indexes? Could you talk a little bit more about that? And is there a performance impact on queries that use one or more secondary indexes?
Yes, great question. There are laws of physics here. As engineers, we understand that. So secondary indexes is actually a very old feature of the software. So this blog, for example, goes into extreme depths of why secondary indexes are important and how they actually function in under the covers. So there is by default, the secondary index is actually a distributed transaction, the same two-phase commit distributed transaction I talked about. We also offer a slightly relaxed secondary index semantics where a failure of a secondary index update can also be sent back to the client for a retry. The default model is the database will do both the commits of the primary key and the secondary index key on your behalf, and that obviously leads to more work on the part of the database, especially if the nodes are geo distributed, for example, right? So it's up to you as a application builder to determine as to in the spectrum of data modeling constructs where you actually lie. Is it complete KV with no secondary indexes? Semi-relational where the relationship is between primary and secondary index key only, all fully relational where the entire relational algebra is at your disposal. And clearly there is a performance change as you go to more and more complex modeling in a distributed form factor.
Okay, thank you. All right, here's the next one. This is from Dennis, who asks, basically he says this scenario. So what if the whole Rancher instance were lost, Yugabyte config and Longhorn config are lost too? Could you fully restore just from the S3 backup, or would you need the Kubernetes snapshot as well?
That's a good question. I think the volume information doesn't capture the Kubernetes metadata. So clearly, yes, if the entire cluster goes away, then you need to have taken a backup the Kubernetes metadata using whatever tooling is necessary in order to recreate the cluster altogether.
Okay, thank you. Okay, here's the next one. This is from Bernard, who asks, how can you migrate an existing Postgres SQL database cluster replication managed with Postgres PG pool to Yugabyte?
So you will not be migrating replication anything on that, right? So you will be just taking the application that was using Postgres SQL language, it's the grammar, and its client driver, and pointing it to Yugabyte. Now, that is where, and replication will thereafter be handled by Yugabyte automatically. So the replication architecture has actually no impact at all. Purely whatever application logic you have written is the question. That's where, whether Yugabyte has every feature that you depend in your Postgres code, that is the question. And I mean, we have a Postgres compatibility page. You can go in, look it up, and see whether all the language constructs that you need are there. If not, you have to make some code changes, and that's where we can help. If you come into the Slack channel, give us a holler. We're ready to help on how to make those changes.
Okay, thank you. All right, here's the next one. This is from Barbaros, who asks, how does Yugabyte DB compare with Spark SQL?
Spark SQL. Okay. Spark Streaming SQL. Now I got it. They are completely different purposes, right? So Spark SQL is for essentially doing stream processing using SQL language on top of streaming data, the data that is continuously moving, being ingested into something like Spark itself, with with, let's say, you have your data somewhere else as the primary store. It can be an HDFS or a Cassandra or something like that, right? Yugabyte DB is your source of truth database, like Postgres, MySQL, Oracle, SQL Server, and so on. So uh, you can use you can bring in data stored inside Yugabyte DB and then use our Spark connector. We actually have a Spark connector. I think, let me show you quickly. Develop ecosystem integrations, Apache Spark. So you can use our Spark connector to bring in data into Spark, and do your sort of the processing inside Spark to compute, let's say, large scale aggregations, um, and then you persist the aggregated data back in the store. So it is not a replacement for Spark SQL. It is complementary because they are at two different layers of your infrastructure. One is for stream processing, another is it for persistent storage of transactional data.
Okay, cool. That makes sense. Thank you. All right, this next one is from Claudio, who asks, if a Yugabyte DB server is not scheduled together with a master and a network split happens, does the server stop serving?
No. So, well, if the client has been previously talking to the Yugabyte DB tablet servers, then there is no impact if there is a network partition to the YB master. But if it's a net new uh, client which has never ever talked to the database cluster, then the need for YB master to provide the current shard metadata becomes important. As a result, the client won't be able to connect.
Cool. Okay, thank you. All right, here, this is the next one. This is from Emil, who asks, and thank you for this marathon of questions, Sid. Really appreciate you staying on.
Great questions.
Yeah, we're coming towards the last few. So this is from Emil, who says, does the sys catalog maintain transaction history per node per system?
Wow, that's a good question. I don't know the answer to that. That's a question. If you can join our Slack and ask, I'm sure one of the engineers will know the answer. I'm just a product guy. Sorry.
Cool. All right, no problem.
But that's actually a great feature if we don't have it, we should have it.
Okay, cool. All right, this next one is from Dominique, who asks, is it theoretically, he says, is it theoretically possible to use Yugabyte DB as the control plane database for K3s?
Yes, I have had this question before. It is possible. Um, Again, it goes back to how it has been, how the K3s schema has been modeled and what exactly constructs it is using, but it is absolutely possible, no doubts about that.
Okay, great, cool. All right, let's see, the next one. This is from Dennis, who asks, how does Yugabyte performance perform against native Postgres and Redis? Does it rely on having more nodes and therefore more speed?
That's a good question. So we actually don't compare ourselves against single node databases or Redis, which is arguably not even a database. It's an in-memory data structure server. Because if you're all good with a single node Postgres and all, then you'll probably never pick, and you should never pick Yugabyte. I think that is not, I mean, people don't pick distributed systems just for the fun of it, right? It has to solve an additional, core pain, and that core pain comes from either you need essentially native failover and repair, which comes by using, instead of a master slave pair, you are using a 3-node cluster where all the nodes are exactly the same, and you lose one, the remaining two heal to take over the reads and writes of of the leaders that were lost. Or it has to do with, you want to horizontally scale, you want to actually add more nodes and gain more throughput in the system. So if we go back to our blog, then there's a performance benchmarks section. So we, as you can see, we have been continuously improving performance in Yugabyte DB over the last few years. For example, this one is sort of an extreme situation as to how you'll do I think it's 1 million inserts per second using the SQL API in the system, right? So we haven't done much performance benchmarking against a single node Postgres because it's a little bit unfair. There is no I mean, in distributed database, the number one challenge is the network. The network is not our friend. It is essentially the enemy, and as database designers, we have to account for that in the design and in the write path, in the read path, and so on. Postgres doesn't have to do any of that, right? So it's a completely sort of it's an apples to orange comparison.
So on that note, so Albert asks, is Yugabyte I think he's asking, is Yugabyte a fork of Postgres, and can we use the same language and tools as in Postgres?
Yes, the upper half of Yugabyte is a fork of Postgres. So that is a very good question. So this post, for example, goes into this one. So what we have done is we've taken the Postgres code base, and we have brought in only the green piece, and we have put it inside every node of Yugabyte. So but naturally we have to wire. The hard work is in the glue piece, where we have to wire it with the underlying DocDB storage engine, and make sure that as we wire up let's say indexes, so we want wire up foreign keys, we wire up various transaction handling modes, various pessimistic logs, various optimistic logs, and so on. So all that has to function A, correctly, and B, with high performance, right? So that is the work that is ongoing. The beauty is that a bunch of Postgres tooling just works naturally. Like if you want to do schema migration with Flyway, or what was the other one, starts with Liquibase, for example, all exactly works exactly the same. If you want to do database schema visualization with dbeaver, it works exactly the same, no issues. So there is a lot of benefit we have achieved by essentially forking the upper half and reusing, but it is not a replacement for Postgres as such. I want to be clear with that.
Right. Okay. Great. So let's just take one more question, and I think we should wrap it up since we're a little over time already. This is from Guillaume, who says, are Longhorn and Yugabyte DB production ready? If not, what's the horizon?
I think I'll leave the Longhorn question to you, Matthew. Yugabyte DB is production ready. We have bunch of users, bunch of customers running the software in production. So feel free to use and let us know.
Awesome. Yeah, and I know that same with Longhorn, that a lot of customers are using Longhorn in production, but that it also is in beta, and it is supposed to go GA early this summer. We also have a Longhorn Slack channel where you can get more info about that, and that's Longhorn in the Rancher user Slack. So why don't we stop there? I think we got to all the questions, but if we missed yours, please apologize. I apologize. There's a ton of engagement and questions here, and then you can join the Rancher Slack and the Yugabyte Slack. Sid, fantastic job. Is there anything else you wanna leave us with before we wrap up?
No, I think I can see from the depth of the questions and also the breadth of the questions that the community is really excited about seeing the marriage of the two technologies. I feel like as infrastructure builders, both on the Rancher side and the Yugabyte DB side, we will continue to work hand in hand to make all these the new reality happen right in front of your eyes through more, I would say, this was sort of an intro lab. We will continue to go deeper and show you more interesting use cases, more patterns, more success stories, and so on. So please stay tuned. And before that, if you face any issues, obviously our respective Slack channels are there to help.
Fantastic, awesome, and yeah, and my email is matthew@rancher.com. So if you do have more follow-up, don't hesitate to reach out. And as we mentioned, this has been recorded, so we will post it on YouTube and send out the link along with the slides to everyone's email, hopefully later today.
And my email is very simple, sid@yugabyte.com. So feel free to send in your questions, and we'll look forward to hearing from you.
All right, awesome. The conversation continues. Okay, great.
Yep.
Thanks, Sid. Have a great week, everybody.
Yep. Thank you.